Good evening, everybody. Unfortunately, my Spanish, although I am Italian, is not good enough, although I love your language, just to do it in Spanish. But let me make a brief introduction, and then you will hear the lecture of Manuel about the real thing, telling you what is Cern and why we are proud that we are turning 60-year-old this year, but we are feeling just to be 20-year-old with 40-year experience. So Cern is all in this triangle. This is the famous triangle of knowledge. At the basis of this triangle, there is our mission, which is we would like just to really push back the limits of knowledge of the nature as it is around us. Just understand why the universe behaves like that, how it started, how it progressed, and how it will continue going. Of course, these are very immaterial questions, but they are questions which are very important because they've proven in the course of the centuries that every time we understand more about nature, then after in 20, 30 years, sometime in a very unexpected way, we always use it just to improve our way of life. There are things that anyway we are doing immediately. We are not waiting 20, 30 years, because in order just to do the experiment and do our research, we need a lot of technology. And often this technology is either not there, or if it is there, it's too expensive. And if it is too expensive, we have just to get smart. And by doing that, sometimes we eat big time. Like, for instance, it happened in 1989 when Tim Berners-Lee was working at Cern at that time in a big experiment. At that time, a big experiment. Now we would call it a medium-sized experiment. Went to his supervisor, told him, I have an idea how just to make communication in our group better. And fortunately, his supervisor told him, well, he's a bit confused, but he's promising, go ahead. And this guy wrote what you are still using today, the language, HTTP, the HTML, which is a markup language which allows every node in a net just to become user of information and provider of information. This has changed our world. If you ask a younger person in this room, since when internet is with us, the web is with us, will tell you, well, the day after Columbus discovered America, internet was there. But it's not true. I am differently young, and I know when it was not there. The other very important and fundamental part of this triangle is the brain of young people, which is at least as important as investment in research, infrastructures, because without the fresh eye of young people, you cannot sustain research. So a place like Cern needs just to train the new generation of physicists and engineers, and we are doing it not by the units, not even by the tens, we do it by the hundreds. And then we enjoy also another very nice thing, is that since we are doing fundamental research, which looks complicated from outside, but is very simple because it's based on a very few rules, which are the scientific method, we can put together a lot of nationalities, avoiding conflicts in religion and politics and things like that. In this moment, at Cern, there are more than 100 nationalities working together. Cern is one of these big ideas for which we should be sometimes very, very proud of Europe. Not every time, but I mean sometime. And it was conceived in the late 40s, with Europe emerging from a devastating war. And a number of scientists thought that one of the best ways just to reunite Europe and also just to avoid the brain drain, which was massive at that time, was through science. And in 1954, Cern was founded under the auspice of UNESCO with 12 European states And now we have grown up to 21 states. The last one just became officially a member yesterday, which is Israel. Israel, yesterday there was the official raising of the flag, because in 2010 the Council decided that in order just to be a member of Cern, you don't need just to be a European country. Again, science as a message of international collaboration, global collaboration, and hopefully peace. Look here at the distribution of Cern. Cern is essentially has a large participation of Europe, but if I go back to the previous slide, you will see that the number of people paid on the payroll of Cern is about 3,500. But the important thing is that there are almost 11,000 users coming from all the world. We are a big village or a small town, if you like. And you see the distribution of this, and the member state, Spain, is doing pretty well, not only in user, but also as a number of staff, fellows, and students, which means that there will be Spanish physicists and engineers have played and are continuing just to play key positions in our environment. This is another very good news, is our age distribution, which tells us that we are doing very well, that the part that we are telling that we are doing training, because the peak of the age is at 26. There are two good news, as a matter of fact, in this plot, is that one is that the peak is at 26. The other is that physics is making your life longer, because you can see there are still people in the 80s which are very active. And this thing, there is one guy who was there was at 85, and I still know this guy. This is a survey of 2009. We are doing the new one. He's still there. He's now more than 90. He has also a Nobel Prize. Of course, all the people who are coming in, they don't stay in the field. I would say more than 50%, after their training, they go and do other things. And they end up in enriching a different aspect of the society, industry, consultancy, banks, research, private research, bringing in a thing which is very important, because it's a mentality of working in an international environment, working in a very competitive and at the same time collaborative environment. And these, in my opinion, are one of the best values that Cern is giving back to the member state. So what we are doing, essentially our mission, is all in this thing. This is a description of our universe. Our universe was born about 14 billion years ago out of a fluctuation of the vacuum, a Big Bang. And it has now expanded up to a level of 10 to the 28 centimeter, which is a big number. It's 1 and 28 zero after that. And the only way just to understand it, some time ago, I was told that if you express it in meter, is the square of the American debt in dollars. Essentially, there are two ways. I was just to explain you why we are so fixed with this idea. If we want just to understand the universe as it is now, we have just to try just to understand how it was when he was very young. And the reason is that when he was very young, he didn't have enough time just to differentiate itself. So it was showing us all its basic symmetry, the basic functioning rules, and that's why we would like just to have a time machine. And fundamental science is essentially building time machines. And you can build time machine in two ways. Let's go to this, is the same picture in a ruler. This is a special ruler because every tick in this ruler is a factor of 10. So these are the dimensions of the universe, which is 10 to the 28 centimeter, which I've described you if you want just to envisage it as a big number. And this is the dimension 10 to the, is a very small dimension, 10 to the minus 32 centimeter, which is let's say, the strength, the length of a primordial string, whatever you want just to, is a sort of thing that near the beginning. And of course, we are putting ourselves is a smart ruler because our scale, which is the scale of the meter, is in the middle. So for the day, I think I will put in the middle of the universe our host here. So for the day. So there are two ways. If you want just to go back and study how the universe was when it was very young, you can look at distant objects. The more distant you look, and the more backward you go in time. Because if you look at a galaxy, which is 1 billion light years away, since the information travels a maximum at the speed of light, you are looking now at the universe as it was 1 billion years ago. And the more distant you look, the more backward you go in time. But you arrive at some point, which is located about 380,000 years after the Big Bang, in which the universe was so hot and so dense that all the light which was emitted was reabsorbed, so was not transparent. So you have a sort of wall in which you cannot just go beyond that. To go beyond that, there are many ways in which instead of looking at light, you look at other messengers with these beautiful things. You will get the lecture after that, you will get a few examples. But you can do also another thing at home. You can fabricate at home a small Big Bang. Of course, you cannot afford the bill of the power, so you do it for a tiny lapse of time and in a very small volume. But essentially by eating beams of a very high energy, you are reproducing in this small time the conditions which were near the beginning of the universe, and the highest is the energy, the closer you go to this beginning. Now with LHC, we are studying the universe as it was a millionth of a second after the Big Bang. And this is very important because in this way we can recreate particles and conditions which are no longer present in the universe, but needed just to be formed like that. So, this is easy just to say conceptually. It's a bit more difficult just to make it in real life, because in order just to do that, you have just to create the biggest scientific enterprise mankind has tried up to now, which is the LHC and its experiment, which is way more complicated than making, for instance, sending a man to the moon or things like that. So, this is 27 kilometers of a superconducting ring kept at the temperature of only less than 2 degrees above the absolute zero, and 4 large experiments, which are the eyes. The machine is the microscope, and the experiment are the eyes which they look at this collision and study this particle. And we were lucky with this machine because, as you might know, in 2012, last year, we had the evidence of this thing which was sought for many, many years, was conceived in 1964. It took us almost 50 years just to prove that this vision that a number of theorists had, nature had decided that this was the right vision. And this was recognized as a very important historical thing, for instance, by The Economist, which is not a science journal, but nevertheless, it recognized that this was not a leap for physics, but for science in general. And this was also recognized by some people up there in Stockholm, which made Peter Higgs and Robert Engler very, very, very happy. And then made also us very happy, because in the motivation was written clearly that this was because Cern exists. Of course, you know, you would ask, yeah, it's very nice, but we need also just to, we have a crisis, so we need just to have things that can be used now. And we think that we are, despite the crisis, doing things that we are using now a lot, because we are accumulating a lot of knowledge in front technologies, which can be used, for instance, in medicine. And I could stay here all evening just to tell you how many of the things that are now done in modern medicine are coming from particle physics. But just one for everything is the fact that we can treat tumors in a much more effective way and less damaging way than using gamma rays, by using protons or light ions. And we can have a better and even improving imaging based on the detectors we are developing for studying our particle. Not to talk about computers and computing grid, which is one of the paradigms which have changed the web into, which is a change of information in exchanging of computing power. I want briefly also just to tell you that the part of the training is taken very seriously, because we are starting from the beginning from a high multiplication type of material, which is teachers. We are training more than 1,000 teachers every year at Cern, because a good teacher will motivate thousands of students. And these are the basis, these are our agents in the society. And Spain is doing reasonably well, but it could do even better. There are countries who are essentially investing in this program, which is not very expensive, because CERN supports it partially. And the nice thing about this program is that teachers are coming there, are being trained, and they bring back already ready material for their students. And then we have this summer student program. Every year we collect 250 youngsters at the beginning of the university, before they decide what to do when later in their life, and we keep them almost 3 months at CERN, embedding them into the research environment. Spain at CERN has a long tradition and is doing very well. Is doing very well in several experiments. Is doing very well from the point of view of the contribution, intellectual and factual contribution, but is doing also very well in the fallback to the industry here. So this, in the picture you have seen at the beginning, when you see one of the large experiments, Atlas, with the small physicist in the middle, and there are these gigantic coils. These gigantic coils, which are 25 meters long, 5 meters wide, 2.5 meters tall, have been fabricated here in Spain, and is a thing that is very high-tech, because this thing have just to have very high vacuum. So all the welding of this thing require very high technology, which was established through the collaboration of CERN, and which now helps this industry just to be one of the leaders in Europe. And there are very many other examples. The other thing is that despite crisis, Spain succeeded with the help also of the infrastructure of CERN, just to increase the number of students, of application, of successful application, just to come and do training at CERN. So I want just to terminate my presentation here and leave the word to Manuel, because it will take you into the real part of the business. Thank you very much.
Okay, I will start by apologizing to Sergio Bertolucci, because my Italian is not as good as your Italian, so I don't think that I am going to give my seminar in Italian. I will switch to Spanish, if you don't mind. Muy bien. Bueno, yo querría empezar.
I would like to start my presentation giving a token of recognition to CERN and to BBVA Foundation, to Bilbao Vizcaya Argentaria Foundation, for this kind invitation. It is for me a great pleasure. It is for me a great honor. This is a great initiative to organize this cycle of conferences regarding particle physics, what we do at the CERN. And that's a great initiative. But this is the right time, right place, right moment, because as Sergio said, This is the 60th anniversary of Cern. So Cern is 60 years of age, and this is a great moment to get together to talk about fantastic results, scientific results in Europe and worldwide, thanks to Cern. I'd like to give a recognition to BBVA Foundation with a long tradition of giving support to sciences like Frontiers of Knowledge Awards and awards given by the Royal Society of Physics, sponsored by the foundation. And I would like to make a disclaimer, that is, that to summarize the history of the discovery of elementary particles of subatomic particles in 45 minutes or 1 hour, it's a huge task. It's something that I cannot do. So what I'm going to try during my lecture is I'm going to make you become curious. I would like to motivate you to attend the very wonderful lectures where great experts will elaborate on what I'm just going to mention here. I'm going to give the flavor of what they're going to elaborate on afterwards. As we know, Aristotle, who was optimistic 2,400 years ago, made a statement, and it was daring. He said that all men by nature would like to know more. But then he realized he went too far, and he said, well, not all, but a great part of men. And he said, the ignorance will affirm that wise people will have doubts and will give it a thought. And since old Greeks, we've had a civilization where we have experts, people, wise people, thinking about important things, like the origin, the evolution of the universe, the origin and the evolution of life and of consciousness. And what I'm going to talk now about is following what Professor Bertolucci has mentioned. I'm going to elaborate on the universe. What is it made of? How was it created? And the way the universe has evolved. We have different scientific disciplines presenting the subjects, like astrophysics, elementary particle physics, nuclear physics, as well as cosmology. Steven Weinberg, Nobel laureate back in '78, one of the ones created the Standard Model, said that the effort to understand the universe is one of the very few things that lifts human life a little above the level of farce and gives it some of the grace of tragedy. Well, let's not go too far, but that's it. And then what is true is that along the last 100 years, we've learned many things in what regards microcosmos and cosmos. Fortunately, there is room for improvement, for getting knowledge to fill the gap in order to know what's ordinary and what's extraordinary. Sergio has made my task very easy. Let's, as we see here, the universe, almost 14 billion years ago, due to mechanical quantum fluctuation of vacuum. There are here the electromagnetic radiation. 360,000 years after the Big Bang, we have like a snapshot of the baby universe. Regarding the microcosmos, and this is what I'm trying to elaborate on, the most important message I'd like to convey to all of you, probably to some inhabitants from other countries, is that matter does not fill up all the space it occupies. What we've learned along the last 100 years is that the atom, which is the basic structure in order to construct the universe, the atom essentially is void. The dimension is 10 to minus 4, 10 to minus 8 centimeters, but the dense part, the important part regarding matter of the atom are nuclei, and that's 10 to minus 12. And till now, we've tried to understand this, and we know till 10 to minus 17. But we don't know that in the future research projects along the next decades will see that beyond that structure, beyond 10 to minus 17, there could be some other substructures, more fundamental substructures. What has happened is great progress in getting knowledge, learning more. How about the ingredients, the basic ingredients of this formidable process of learning more? And I'm going to talk about the microscopic world. There were huge theoretical advances, technological, spectacular progress in several sectors of our instrumentation, and it's been possible to construct huge facilities, what was never envisaged in the domain of fundamental sciences, basic sciences, and those are global efforts and getting knowledge together. Particle accelerators played a very important role since the mid-50s on. That is, since the moment when the Cern was created back in '54. And why is it so that studying processes generated at particle accelerators, why is it so important? Because of the dual nature of the when a particle moves at a given p energy, there is the wave associated, and the wavelength is getting the capacity to solve structures spatially. That is related to the Heisenberg equation. If we have here, like at the Cern, beams of particles accelerated up to energies like 1 tera electron volts, which is the equivalent of 1,000 times the mass of a proton, we have a microscope with a space resolution that's 10 to minus 18 meters. That means that we can discover, we can see, we can look scientifically inside the matter at the scale, the microcosmos, at the we're going to be able, when we will have the Large Hadron Collider in 2015, we will get resolution, space resolution that will be 10 up to minus 23 meters. It is very important to study this. Professor Bertolucci mentioned how important those processes are, and we have to study this at a very high energy with high energy beams, because with a thermodynamic relationship linking the energy at a given process with the universal time and studying processes of high energy, we're establishing rules that govern the universe, the evolution of the universe at small time scales. And when we conduct our experiments with the proton collisions at the Large Hadron Collider, we're establishing rules that governing at that time the universe, that were ruling the universe as a baby universe. And when we have those collisions, we are disclosing the rules when the life of the universe was at 10 microseconds. If we were able to know about it, and David Gross, the Nobel laureate, was one of the experts discovering the quantum cosmodynamic. He said that the most important product of research is sometimes ignorance, because when we try to know more, then we know how many things we do not know, and then we know the level of well, what's unknown. And what do we know? Well, there are lots of things we don't know. 95% of the universe we don't know. What is it made up with? And we have here astrophysics, astronomic measurements, and the very interesting studies on the microwave background radiation, studying supernovae, and studying the morphology of galactic cumuli, this in the light of gravitation, general theory, and the concordance cosmological number, we can measure the balance of energy and matter in the universe. Only 5% out of the total is made up of particles we've studied in detail at the lab. So we only know 5% of it. There is a 25% of the total amount that is constituted by a matter that is not absorbing, not emitting magnetic radiation. It's not visible. It's a dark matter. That's the name, but we don't know what dark matter really is. And we know that the universe is expanding. It's that acceleration, expansion. And the underlying reason of this process of expansion, this growth, is due to perhaps dark energy. We know the equation of state, but we don't know exactly what it is. And what do we know? Well, we have here, 5% is what we know. 100% minus 5%. 95% is unknown. 5% is known, and we have architecture that was proven, which is the standard model of the particle physics. Einstein said that the main challenge of a physician, of a physicist, is to know the elementary rules out of which the cosmos could be made out of a deduction. That's what a physicist has as a great challenge. The standard model, which is a synthesis of knowledge, will allow us to construct in detail how does the universe or the microcosmos work. How about the rules? How about the laws ruling the way it functions? This is a very elegant structure based on simple ideas, rules that are controlling processes among elementary particles can be obtained when we talk about invariant. Laws under transformations given a determined symmetry group. Which is a group? Well, that's a challenge. That's one of the main scientific contributions along the 20th century. This is a simple structure, simple theory with a huge predictive value with three pillars. First of all, invention and discovery of quarks. Now, in 2014, it's a 50th anniversary, the description of different phenomena, like, for instance, electromagnetic and the weak forces phenomena, like radioactivity, and how energy is produced inside stars, and understanding strong forces, the strength that guarantees the cohesion of nucleons. And we have here matter and several forces, and there are interactions. It is like matter particles will get associated to the particles of force. And in the model, the standard model of particle physics, we see electromagnetic phenomena, different phenomena regarding the intensity, regarding the range of action or scope of action, and it's different in the case of weak forces, energy inside a star, radioactivity. They have the same origin. All of those phenomena have the same origin. This unification of several phenomena, considering electromagnetic phenomena, considering the weak force mediated phenomena, they are as important as identifying the inertial mass or the gravitational mass that was proposed by Newton at the end of the 17th century, or what Maxwell did propose in the middle of the 19th century when he said that electromagnetic, like electric and magnetic phenomena were of the same raison d'etre. And the model, the standard model, has a specificity. All particles in principle should be, well, of zero. This is very important. That hasn't been confirmed. All particles I've mentioned before, most of the particles have mass on top of the, well, we have gluons having a mass that's zero and graviton that has mass zero. Those are exceptions, but particles should have a mass. And that's a tragedy. That's a tragedy, and it was said that the great tragedy of science is when a beautiful theory is contradicted by a very unpleasant thing, like having particles with a mass. All the people you can see here, Engler and a person who died a year ago, Peter Higgs, and all of those in Hagen, they proposed a solution that was a solution for this important problem. So, Keeble, Grolnik, Hagen, Englert, Wood, they proposed something prior to the establishment of the standard model that was created back in 1964. What I'm mentioning here seems to be simple. The standard model is rather complex in details. That the picture of some of the interesting equations, and here people that did play important roles developing the standard model. As we said, and as Professor Bertolucci said, after many years of huge efforts, and I will mention this at the end of my presentation when I will talk about Cern contributions to knowledge. Well, 4th of July 2012, it was presented at the Cern, solid evidence to affirm that a particle with properties similar to what has been predicted as Higgs boson was discovered at the ATLAS experiment and at the FMS experiment. So the Higgs boson is filling the gap in knowledge of what's ordinary, that 5% of matter and energy. There are other pending problems, unsolved problems, but our colleagues and friends will elaborate on this along the cycle of conferences. The discovery back in 2012 was a milestone mentioned by the journal Science as the most important scientific item along the year. And then the Príncipe de Asturias Award was given to those three, Englert, Higgs, and the Cern. And in December, Peter Higgs and François Englert, they obtained the Nobel Prize in Physics, and it was mentioned how important Cern contribution was, and the ATLAS and their experiment were crucial, vital for their achievements. And they got this important award due to their ideas proposed 50 years ago. How come we've learned what we've learned? How was it constructed? How do we have the experimental construction of the standard model? I would like to say that along the first half of the 20th century, what was discovered by Hess back in 2012 was the main tool to establish the existence of new particles, more particular the antimatter and the particles that are decisive for the formulation of the standard model. Antiproton, the second antiparticle discovered in '55 at Berkeley Lab in California. That was a milestone, a very important inflection point. We see here a turning point. accelerators took the role, but of course there is a lot of science to develop regarding neutrinos derived from the sun, cosmic neutrinos, dark matter, and to know more, to know in a better way the differences regarding the properties of matter and antimatter properties. And here we see that till 55 all elementary particles were discovered, as we see here, according to cosmic ray studies. And we have here the study of cosmic rays conducted at big observatories. At the beginning, there was the first half of the 20th century. There were then many important experiments like the Auger experiment in Argentina, but the first evidences of the existence of those particles were situated in Chamonix, Le Pic du Midi, and also in Chamonix, and also the French Pyrenees. And then from the 50s, big labs were created with lots of particle accelerators. The first of those was the Berkeley laboratory, the Lawrence laboratory, that started back in 31, the National Laboratory that started in 47, the German laboratory near Hamburg in 59, SLAC in Stanford, and back in 62, Fermi Lab, 67, and the Cern in 54. So there are other interesting efforts, some labs in Russia, some other labs in Japan I'm not going to mention. I'm going to review, without giving many details, the history of discoveries, because summarizing what has been discovered in order to validate the standard model, that is a theory describing the processes at microscopic scale, has been a very long pathway, very difficult, with lots of difficulties. And I would like to mention here several steps, different periods, and I would like to mention those periods. First of all, what I will call La Belle Époque. The fantastic period is 1/3 of the 20th century, initiated by the discovery of electron in 1897. Radioactivity was discovered, all phenomena were discovered. The discovery of the atomic nucleus by Rutherford in 1911 with a technique. The atomic nucleus was discovered in 1911 with collision of particles at a given energy with fixed targets. And years after, they discovered the nucleus of the atom of hydrogen, which is a proton. And in 1932, Tolwick discovered the other important element in the formation of nuclei, that is a neutron. And regarding instrumentation, it was invented, the device invented by Wilson, ray cosmics were discovered, and the first cyclotron was constructed. Theoretically speaking, then there was a solid ground to stand on to create theories trying to describe phenomena at a microscopic level. The restricted relativity theory establishing the relationships regarding mass and energy, and a new relationship, space-time, and the general theory of relativity establishing the relationship, the geometry of the universe and the mass distribution within the universe. Einstein did formulate that photons will have a corpuscular nature. Quantum mechanics was developed, the solid ground for the theory of particles. Dirac, when the equation was proposed, was the existence of one antiparticle, and Pauli there established the existence, or proposed the existence, of neutrino in 1931. It is interesting to point out that when Dirac in 26 made his theory and proposed the creation of electron, scientific circles thought it was just something academic without any repercussions, without any application. So they thought positron emission tomography is one of the consequences of that information that is possible to create antimatter, to produce antimatter. Same things with neutrino. Pauli proposed this, and now, well, they thought it was just prevent violation of a conservation of energy, but neutrinos are fundamental ideas to know energy generation inside the sun. And we have pictures here. I'm not going to elaborate on the pictures. We have here the leaders, the creators, the pioneers. And here we have experiences required, people, pioneers going up to 8,000 meters high to show that the ionization wouldn't decrease with altitude, but on the contrary, that did increase, and that was due to an external source coming from external space. Lawrence was the first one developing the particle accelerator, that is a small one, 1 meter wide, 1 meter diameter. The LHC, or the LEP, the circumference is 27,000 kilometers. And so those accelerators constructed by the experts and workers were tools, devices designed, constructed to explore the nature, the microscopic nature of matter. But nevertheless, today we have 20,000 particle accelerators, out of which only some of those are used for basic or fundamental research. All of the others are used for practical industrial applications, for medical fields mainly. Particle accelerators are methods, strong methods for given therapies in the case of cancer tumors. So in oncology they use particle accelerators. And the second level, which is the Middle Ages, that's how I describe it. And we have here a very exceptional scientist, Fermi, proposed the beta disintegration theory, how there will be the proton, the neutron, the neutrino as a disintegration result. And then we have the future discoveries by Pontecorvo. And here we have in 47 how the first quantum theory of fields was proposed, the gauge class, quantum electrodynamics explaining electromagnetic phenomena in a very accurate way. And then there were important discoveries, positron, the important contributions on the existence of a dark matter, the dark universe, that was proposed by the Swiss astronomer Fricke. And here we have the discovery of cascades introduced or produced by cosmic rays. We have the heavy relative of, well, here the muon, and studying the pion was discovered, the first examples of particles, rare particles, and studying cosmic radiation. And in 53 we have an discovery of electron neutrino by Cohen and Rehn in 53, I said. And here we have pictures of the leaders of developing knowledge. Here you see Fermi, and to my surprise, the expression of the electromagnetic constant alpha he describes is not correct. The one that's correct is the one you see here, that shows that even a genius can make a small mistake, mainly when they are just drawing something and using a whiteboard or a blackboard. This is the discovery of the first particle, foreign particle, discovered in 47. Rehn and Cohen experiment that was daring, when you see the flow coming from Savannah River nuclear plant, And it was this initiative that was taken with a pinch of salt because they wanted to study the production of neutrino and nuclear explosions. They had prepared this, planned this to be performed at Los Alamos, with the Ministry of Defense in the US always thinking about people decided that that was too daring and too risky, so that didn't take place. The experts who developed quantum electrodynamics were mentioned. In '54, then there is a good old times, because that's the moment when Cern became the leader in the process of getting knowledge. From '53, '54, they started with the invention of the bubble chambers. There was a betatron construction. There was the discovery of the multiproton. And the group Alvarez at Berkeley discovered lots of elementary particles that were not elementary because of the huge amount of particles that were detected. Then Schwarz-Schönberger discovered the second neutrino. This group where I worked also discovered the baryon omega minus. There was extraordinary phenomenon mentioned by Kronig and Fitch in '64, the violation of one of the symmetries. Chapard invented the chamber of, in '67, he got in 1992 the Nobel Prize due to that, and quartz became a reality thanks to the experiments of the MIT SLAC at the end of the '60s. At the Cern, Vladimir discovered the stochastic cooling of protons, and in '73, Lagaric, Muset, and Garnell discovered a new essential process for the formulation of a standard model, neutral currents. Regarding theoretical viewpoints, we have here the hypothesis that parity is the violation of a symmetry in weak processes. It was Dr. Wu who discovered experimentally the existence of the phenomenon. Gell-Mann, Nyman, Zweig proposed a system in order to classify the multitude of particles stemming from acceleration of particles and experiments, and as a consequence of the classification, the idea of quarks was proposed by Gell-Mann and Zweig independently. As I said before, Borg, Engel, and Higgs proposed the mechanism of the breach of symmetry, electroweak symmetry, and the standard model, and that was formalized by '67, and then there were theories by so in '67 Stephen Weinberg invokes the Higgs mechanism. In '73, physicists working with the Gargamel bubble chamber at Cern observed neutrinos, and neutrinos undergoing neutral current scattering, and then Gross and Wilczek did formulate the quantum theory explaining processes that are responsible for nuclear cohesion. Here we see the bubble chambers. We see on the left the big bubble chamber at Cern, the antiproton discovery. Luis Alvarez, laureate with the Nobel Prize in '68, did huge chambers in Berkeley. He discovered the part of those elementary particles, so to speak, zoo. And here we have the proposal of a system for classifying the particles. The name was Regimen, who got the award in '64, and they talk about the Buddhist proverb presenting 8 conditions for avoiding and stopping pain. And here we have a new quantum number that was proposed in '53. The quantum number proposed in '53 by Gell-Mann and Nishima, and it was possible to classify particles that were discovered at the representation of this group of symmetries. The first big, I would say, confirmation of the classification was obtained, or it's due to Professor Samuel's group. Here I am when I was young with him, and here we have an excellent contribution, and here we have the particle that was part of this classification that did consolidate the symmetry scheme, and in base of the scheme, Gell-Mann and Zweig did formulate back in '64 the theory of the existence of elements out of which it was possible to construct all particles, all classified particles. Well, quarks, as the name was suggested by Gell-Mann, reading a book that is impossible to understand, is Finnegan's Wake by James Joyce. And he thought those entities out of which the spectrum of particles is constructed were just quarks, were not real entities, because those particles, those constituents had a fraction charge, and experimentation did show that experimentally, well, there were no fractional charges, but Zweig went to Cern and gave a fantastic lecture, proposed the existence of the aces. And aces, he thought those fundamental elements were real, and that sooner or later there will be a confirmation of this in an experimental way. And those fundamental constituents, well, particles discovered had a very simple way to be understood regarding the composition: quarks and antiquarks, regarding mesons, and in the case of baryons, 3 quarks. And here we have a picture where we see the physicists having discovered the second neutrino, Dr. Pontecorvo. We have a picture where we have Fitz and Croning having discovered that particles and antiparticles and Dirac formulation should have all properties, mass, spin, everything in the identical mode. That was not the case in those rare particles that had been discovered in the cosmic rays, but that were studied in acceleration of particles as experiments. There were differences, there were discrepancies in the way of the decay, and it was a 3 out of 1,000, a lack of concordancy or consistency. And let's go back to the origin of the universe. If it started with a Big Bang due to a quantum fluctuation, prior to void there was nothing. And how was it produced? If there are particles, you should have antiparticles to have the net balance equals 0. But the part of our galaxy that we observed shows that there is no primitive antimatter visible. How is it so that in this process of expansion of the universe, how is it so that they were produced? This transit from a symmetry and in a matter and antimatter, how is it that this did evolve towards a totally antisymmetric situation where you only have matter? What happened with the primitive antimatter? Well, Andrei Sakharov, the famous physicist, and he was always fighting for peace, he established that the origin of the disappearance of the antimatter could be explained by the microphysics, and one of the law is the effect discovered by Croning and Fitz. Unfortunately, the magnitude of those deviations, diversions detected by fish and in the case of other particles are not enough to explain the phenomenon. This is why there are things pending, many things there is room for improvement, and many things to discover. Reality of quarks. I did mention that there were people skeptical on the real existence of quarks. And it was the experiment at Stanford lab back in the 60s where the structure of matter was discovered. Inside protons and neutrons, there were particles that were responsible for collisions and behaviors of electrons at a moment of collision with matter. The experiment of the MIT SLAC that took place in 67 up to 70 were to collide electrons against protons, but with high energy electrons. And here we have the Rutherford experiment at the beginning of the 20th century. Instead of using electrons, he used particles, alpha particles, but unfortunately low energy alpha particles, 7 mega electron volts. So he reached what he could show, that it was 105 times, the nucleus was 105 times inferior to the radius, so smaller than the radius. And there were many experiences, and in 61 this scientist got the Nobel Prize. He did show that magnetic momentum, they have this distribution. That was the MIT SLAC experiment that was fundamental with the seminal contributions. Here we have those who got the Nobel Prize back in 80 were the theorist Yorking from SLAC that did help them to interpret the result of measurements conducted with this huge spectrometer, showing that there were punctual entities inside those nucleons. And then we have here the revolution of the month of November, validating the standard model of elementary particles, discovery of electron tau, quark B, quark C, muons, spectra, the discovery of bosons by van der Neer at Cern, the construction of LEP, the validation of a structure in quantum mechanics that underlines, in the case of electroweak model for discovering radioactive connections, the discovery of quark T and the Tevatron, Fermilab in 1995, where Serge had a fantastic contribution, and as Sergio said, the invention of the World Wide Web. Those are very important contributions, and this is not directly related to elementary particle physics, but the discovery of the anisotropy of the microwave, as we see here, cosmic radiation, allowing us to understand why and how the universe is made up and how it was as a baby universe when it was only 400,000 years old. And here we have important experts, and here the contribution in 1998 when neutrinos had a mass that was not zero, the acceleration of expansion of the universe, the construction of a large hadron collider, and the discovery of a confirmation of the Higgs boson at the Cern in 2012. And I'd like to give recognition to all scientists and to remind you that with the discovery of a Higgs boson, we've filled the gap of what's known on the ordinary, but there are pending things like knowing more on neutrinos, the hierarchical structure of masses, to know more, to try to know the nature of dark matter, and to know why and what are the processes making antimatter disappear on the evolution of the universe. Cern, and the most important statements been made by Serge. We have the best group of accelerators worldwide with experimental programs that are incredibly good. And how about contributions by Cern to the process? Well, we know that we gather knowledge and we go forward, knowing more the microscopic world in a very many ways, establishing the spectrum of particles that I've mentioned, the hadronic spectroscopy at the Cern from 60s There were programs on, really very strong, very potent programs allowing us to discover lots of particles. Also, there were many progress, gigantic steps forward. The beams of neutrino with high energy, the Schallback cameras, the cooling, stochastic cooling that I mentioned, the World Wide Web invention, but at the same time gathering more and more information, discovering new processes, or studying in a detailed way processes that were rarely seen. The discovery of neutral currents and the discovery of bosons, the W and Z bosons, and thanks to the discoveries, Van der Meer having invented stochastic cooling of protons, and Carlos Rubia, who was the driving force underlying the process. Then the W and the Z were discovered. That's a great validation of the electroweak standard models. But there were models, studies with neutrinos, studying phenomena and completing the Matisse-Lac experiments on quarks reality, studies on the reach of symmetry in a very accurate way, and with wide range of conclusions, variety of neutrinos, the elementary constituents, and the discovery of the radioactive corrections, lots of details, nuances that are validating the standard model. Last but not least, the discovery, as we see here, of a confirmation of Higgs boson. And to put an end to this with a large hadron collider, we have here the main objective, scientific achievements. It's been a global process. Many countries, not only countries pertaining to Cern, but America, Canada, people from India, people from many countries. But it's been a very long process, very demanding, with savoir-faire required that's been exceptional, and then unifying criteria, going along the process hand in hand, and that's been managed by different rulers, different administrations, different governments. And here we see the complexity of the process and how huge and great the process is. Construction, assembling this at the tunnel, the participation of Spain, constructing the device, 1/3 of the cryostates of the 1232 dipolar elements were constructed in Spain. 1/3 of the cryogenic line where superfluid liquid helium circulates, and that is cooling down the magnetic elements, and it's only 2 degrees on top of the absolute zero. And here we have one of the 2 experiments allowing us to discover the Higgs boson, area 5, and 2000 superconductor elements, magnets. Experiments mentioned by Sergio were conducted by lots of scientists. That's a picture taken from the experimental part. This is we see around 20% of those having contributed, and that means 3,000 people, 3,000 researchers. Great experiments. Atlas, 7,500 tones. Here, 14,500 tones, even though it's called compact. They are beautiful, and on top of this, we have the representation of the opera Les Troyens de Berlioz of Valence, in Valence, that is inspired in Atlas. We have those big structures that were mentioned by Sergio. Those were structures constructed in Spain, and Also, we have Spanish groups, Spanish industries working hard and going hand in hand forward with top technology in the construction of the devices. He mentioned also the GRIV we have here. It's a next step after World Wide Web, having access to distributed information. But the computation grid allows us to have access to distributed data and the possibility of processing data at different facilities, geographically distributed or scattered. When they ask me, I always think about the classics, and Niels Bohr said it's very difficult to think about the future and predict the future. Thomas Morgan said it was difficult enough to know about the past. It was impossible and cumbersome and difficult to know about the future. Standard model construction required huge efforts, 50 years of efforts. 40 people got to the Nobel Prize. It was great success. It will be successful, and some of our colleagues will explain this at other lectures. There are pending subjects. There are many ideas, multitude of theoretical ideas in order to go forward, validating the standard model. For now, at the Large Hadron Collider, we've looked for new possibilities among new ideas, and that could be materialized. So taking data from LHC for the time being with negative results, but obviously with a lot of enthusiasm and optimism, we'll go forward. The LHC will keep on working for 2 decades, and on top of this, I think that we have to be optimistic. As David Gross said, the fun is just beginning. Scientific fun is just beginning. The process of knowing more is fun, and it's beginning now. And I'd like to mention something, the optimistic approach of Einstein, saying that the incredible thing of the universe is that we're able to understand the universe, and that we don't understand how is it that we do understand the universe. So we need global efforts. We need here one of the paradigms is the science we conduct at Cern. Weinberg is a bit more pessimistic, and he said, well, the more we seem to know about the universe, the less meaning the universe seems to have. Thank you very much for your kind attention.